a reinforcement learning class. Are you also recording?
Yes.
Sometimes I won't have time to check the Discord, so if you notice some student asking a question that I missed, then please tell me. And last time we discussed the grid world, we introduced it a little bit. So we have a robot that can move up, down, left, and right. And the initial state, the start for the robot is A0, this cell here. And then it can move around the environment. It cannot enter or step into an obstacle, so the blue cells are um, illegal to enter. And some of the cells, the robot will receive a positive reward, 99, or a negative reward, negative 64. So this is the basic setup. So when we model this as a Markov decision process, then what are the states that we can use for our robot? Because it generates it randomly. So we can write a function to find the state so that the vector slots are consistent. Where's the then the I can just print the environment. Two one three one two two three two three three. So this is 3 3 0 1 2 3. So 0 is there. And 2 1 2 2. Yeah. Okay. So the obstacles are in row column format. So if ij in obstacles, So basically any cell that doesn't have an obstacle in it is a cell that we can use for our states. So let me just share this again, so make sure that's the link. Port A plus. For ij in states. Okay, wants to join. E0, 1, 2, 3, 4, E0, 1, 2, 3, 4, C0. That's not right. So how come this doesn't trigger here? IJ, this must be a couple. Yeah, then it's correct. Actions, transition function for the different motions. here are all the states that we have the actions, our transition function. At the moment, we assume it's fully deterministic. So for example, the probability of ending up in A1 if we go up in A0 is 1. And the probability of going up in B1, ending up in B1, ending up in C1 is 0 because we're blocked by an obstacle. Now, later on, we'll be looking at other kinds of versions of the transition function. Right now, we assume that the agent knows the transition function. Later on, we'll look into algorithms for dealing with the case where the transition function is probabilistic or the transition function is not known to the agent, or both. How come you're not logged in yet? You? Yeah. How come you're not following the class or something? Are you logged into Discord already?
Oh, I cannot. I'm trying to use to log in. I just watch a
Okay. Okay, so I have to change that. So in this environment, like I said, it has the Markovian property, or it is Markovian, because why is it Markovian? What do we mean by an environment having the Markov property? We did that last class. What's important about a Markov decision process as opposed to a Joe decision process or any other kind of decision process? The Markov property discussed previously is, I'll write it there again, it's actually written here. The reward function, state transition function, they only depend on the previous state and the action that we execute. So that means if I look at this environment, if I enter here from the right, if I go right, I have to pay $64. And I always have to do that. It doesn't matter how I ended up in this state A1. So if I went from A0, A1, A2, I have to pay $64. If I went A0, B0, C0, D0, C0, B0, B1, B2, and then to A2, I still have to pay $64. So it doesn't matter how my agent got into a particular state. The path that we went through to get there is not important. So the reward and the state transition is only a function of the previous state and the action that we execute. Now, sometimes we have domains where we actually would like to have a different kind of reward function. So for example, here, this is an example from our previous work on tiny toy cars driving around. And in that domain, you want your controller to be smooth. You want it to drive in almost a straight line there. You don't want it to go left, right, because it makes the robot more unstable. But the state for this particular domain would be the robot is at that position. So if we include a term that says, oh, how much control work we did, or how smooth the control was, then that environment is not Markovian anymore. Because now it matters if I follow the red path to go there, I have a bad value. If I take the blue path, I end up with a good value. So the value changes depending on how I got into this particular state. So that domain then is not Markovian. And then let's have a look at our environment. What we want to draw, or what we want to do is we want to maximize this expression. That's a goal of learning the right policy. We're trying to find the policy pi, the maximum pi, such that the expected value of starting at time t0, running until our horizon time, the discounted reward for the states is maximum. Actually, let me include one part here. We want to say that we have a specific start state. So S0 equal to because we usually have a specific start state in mind. So now I could ask you, how are we going to calculate this particular value then is called the value function for that state. So I want to find for every state this value function. Now, here we include a discount factor, gamma, that sort of models that the sooner we get the reward, the more useful it is for us, the better it is for us. Um, yes. So I try and reduce the number of distracting windows. Because on the Discord channel, it only shows the Google Chrome window. So here's the environment. We start in A0. And now let's figure out what the value function is for this particular environment. Uh, so V star of, pick some interesting ones, B2 is one. And V star of A2, actually B3 as well. then that's hopefully enough. B3, B2, B4, and then B3, A1, A0, and B4. So now we have the following problem. What is the value function, the optimal value function, V star, for these states given this environment? So how about B3, which is the red state? What's the optimal value for B3? Well, the episode will end here, right? So the agent has no actions left. There's nothing it does anymore. So the only thing that will happen is that we get $99, right? Because for B3, unless I get it wrong, B3, we get paid $99 for being in that state. So we got lucky. So we get $99. Okay. A1. Oh no, let's not do A1. B2. Okay. How about this state? B2. This state here. What will be the value, the optimal value function? So the value of this state under the optimal policy, what's the best I can do if I'm in state B2? Go right. And if I go right, then what will happen? Next round, next step, I will get $99, right? Now our discount factor is 1, right? Gamma is equal to 1, which means I still get $99. There's no penalty for getting the reward later or further into the future. So B2 will have a value of 99. And how about B4? Still 99, right? It's the same. Except instead of going right, I go left. How about A1? A1 is here. Right, I still get 99 because I'm operating under the optimal policy, right? So in this state, I don't want to go right and have to pay $64. What I want to do is go up and go right and go right. And in that case, I will get $99 and there's no discount. So that means A1 will be 99 and A0 will be also 99. And B4 also 99. So let's write a function to draw this. Let me change this for if I remember correctly, I think okay. Now, Now let's say I want to draw B. Draw B on the environment. B. And okay, so I don't have to draw this. I have to draw that. And and we only draw it for things that are not obstacles. So if yx not an obstacle, xy, no, plus equal x. So x plus 0.5, y plus 0.5, x string of v y x. Okay, so that seems to be good. Okay, so now we have a different kind of environment. I forgot to skip the. Now I want to be able to see if we can plot it. Draw the environment. Okay, so we have 4 rows, 5 columns. So our D value in this case would be 20, 20, 20, 20, 0, 0. 20, 20, 0, minus 70, 20, 0, 70, 20, 20, 20, 0, 0, 20. And 20, 20, 20, 20, 20. How come my green thing is broken? Oh, print out appends. This list. Oh, this is wrong. And this will be. Oh, yeah, just have to make sure I jump. X, and ah, oh, that's good. X, Y, X. Hmm. I don't even know how this is calculated. Unfortunately, I am too used to the NumPy um, way of specifying the coordinates. So, and this was particularly silly because that code is already in here. I didn't actually have to write that. And this part, this one is correct. I'd written that last class. Okay, so draw the envelope. So here another environment, 91 and 63. And then let's go more. So the solution for this one would be 00 91 91 91 now. 0 0 91, 91, 91, 0. Zero, and then okay. So now we have that. So the same question. We will answer now, but with a different discount factor. So what discount factor do you want to use? Like here's the solution. 0. Okay, so here's our value function, optimal value function. If our discount factor is 1, now we want to use a different discount factor. So what discount factor would you pick to make it easy to calculate?
0.1.
Why 0.1?
It's easier to
10% you mean is easier to calculate? Maybe, okay. Anything that would be even easier? I think it would be even easier, but sort of cheating if we set gamma to 0, right? Because what would the value function be then, the optimal value function? if gamma is equal to 0, then how would these numbers change? Then there will be no reward passed from any future state to the current state, right? Which means that all the white cells will be 0, the red one will be 91, and the green one will be negative 63. So that would be also an easy one to fill out. We have to do more computation for different gamma values, and let's pick a gamma of, I said 0.1, but the problem if you set gamma to 0.1 means then it's going to disappear because we only have 2 decimal digits here, right? 2 decimal places. So I don't want to print it too much. So if I'm 3 steps away, then first one is tens, then hundreds, and then I will see no more impact, no more effect. So we'll pick something higher. So let's stick with 0.8. That should decay not quite so quickly. And then what would be the value function for this environment? So fill in those values. So then what would be the value for A0?
Oh, 0.8 times
0.8 times 91, yes. A1,
91.
91, A2,
0.8 times
yep. 3, A3,
negative 63.
correct? And then B0 is an obstacle, B1,
The same as A0.
what?
The same as A0.
Yeah. And then B1, B2,
0.8 times 0.8 times
0.64 times 91, and then 0. Then here we have 1, 2, 3. Two, 3 steps away, 4 steps away, 0, and then 0, 0. So this is 1, 2, 3, 4. 5, 6. 1. That's a number of steps away, but not the value function. But you can use the number of, one of the students submitted a solution. Quite right. 0.8 to the power of x multiplied by 91. V2 then. So here we have 0.891 times 91, 1 step away, 2 steps away, 3 steps away, 4 steps away, 5 steps away, 6 steps away. Okay. Now, what happens if we have a non-stochastic, non-deterministic? We have a stochastic transition function. And gamma is 0.8, and our reward h is equal to 100. How can I calculate that? So now let's say that the probability of the function succeeding is 0.9. No, 0.9 is not so. Okay, 0.8, but with 0.1 probability we go, so I want to go this direction. With 0.1 probability I instead go to the right, and 0.1 probability I go to the left instead. Gamma is equal to 0.9. And the horizon is also very far. Enough to explore the environment. The horizon sort of is just important. If I set it to 2, then you wouldn't have enough time to get from D4 to A1, so then your reward would be different. But if my horizon is 100, then definitely if I follow actually anything larger than 6, I'll be able to reach 91 under the optimal policy. So in this case, it doesn't really matter what H is, as long as it's greater than the maximum number of steps you would take under the optimal policy. Okay, so for this environment, then what should the values be? So let me just show you the environment again. Here's the environment. So what about state A0? What will be the expected, actually, let's not take A0, let's take, let's take, okay, I'll change this one a little bit to make it a better environment. Um, I just want to remove the rewards. And you'll see in a second why. And the reward coordinates were in this format, so I want reward to 1, 3, -63, and 1, 91. So now it's better. So under the optimal policy, what would be the reward for state B2? For non-deterministic uh, transfer function or non-deterministic domain, where gamma is 0.8 or 0.9. Let's say that one. Gamma is 0.9. Value for state or B value for state B2. In other words, V star of B2 is equal to what? What should that be under the non-deterministic policy? What's the optimal action here in B2? What should the agent do?
Go left.
Go left, right? And what's the reward of going left?
Because they only have 0.8 plus gravity is 6.
Right. So If it's a deterministic domain, we go left, we know we end up left, and we will then have our $91 multiplied by gamma, discounted by one discount factor. But now it's a non-deterministic domain. It's a stochastic domain. So I want to go left, but there's a 10% chance that I go up and a 10% chance that I go down. Right? So what does that mean for my reward value for B2? That means I'll get the 0.9 times 91. I only get that with 80% probability. So that value should be 0.8 multiplied by 0.9 multiplied by 91. But that's not quite correct, right? Because
if it fails, then we will consider C2 and A2.
yeah, I sort of need to know the V star of, what is it? C2 and A2. But that would be with respect to H minus 1 for the next step then. So now one way of sort of thinking about that is that given a discount factor, that effect from going through C2 and going through A2 may be quite small, but actually it'd be more interesting if I move the green to there. Right now, it wouldn't be such a big problem, right? Because the agent, if you look at this particular domain here, then the way that the probability works, it doesn't really make any difference. Like if you're in this state, right, then you will go left. And if you're here, well, you will go up, right? And if you're here, you can go up and to the left, or you can go here and up, and those values are going to be the same, right? So the agent, the policy, the optimal policy doesn't actually change. The reward will change, but the decision that we need to take for each state remains the same. It doesn't need to change, right? But now let's have a look at a more interesting environment. So how about this domain now? Why is this more interesting? Like before in the domain, we switched from a deterministic to a non-deterministic policy, right? But as far as our policy is concerned, it didn't really matter. The actions didn't change, right? But what about this domain?
Also start from B2.
Huh?
We will still start from B2.
We can start anywhere we want. Yes. Or what happens now to the value of B2? That's exactly the problem. If I'm now in B2, then what will be the value of B2? So that would be 0.8 times 0.9 times 91 plus. What happens if the agent is in B2 and goes to the left?
0.1 times negative 63. And
So now we may end up going into negative 63. So now all of a sudden we have to pay a penalty, right? And if the penalty is minus 6,000, then it will be even worse, right? So what should the agent do now? If the green one is very large, right? If that's minus 6,000, so very large value, then clearly what it should do is, if it's in B2, it should
go down.
go down. Right? Because if it goes down, then there's a 10% chance it ends up there anyway. And then the episode is over, so that would be good. If it succeeds, with 80% chance we will be here. And with 10% chance we end up there. Most importantly, with 0% chance we have to pay the penalty here. Now I'm down there, then I can try and go to the right, and then I can try and go up. If I try and go up from here, then it's much safer. Because there's no way that I have to pay this big penalty. I may end up there, I may end up there, then I have to go back and try again. So in this case, the actions that the agent has to pick actually will change. Now whether if this is minus 0.63, then the discount factor here multiplied by the probabilities Here we get 90. If I go from here to there, I get what reward? If I succeed, I get what reward?
0.8 times 0.9 times
0.8 times 0.9. So, but this only happens with 80%. Sorry, 91 times 0.9 is the reward that I get if I succeed, but that only happens with 80% probability. So it's 80% of that. So that'll be about 0.6. 0.6 times 91. So 54. I would expect to get $54. But there is a 10% chance that I have to pay 0.6, 0.5, $5. Now if I go here, this will be discounted by 1, 2 extra steps. But there's zero chance that I have to pay the penalty. So it depends on the difference between those two rewards. Whether it makes sense for the agent to go down and then turn right, or if you just try and then if it is unlucky, it has to pay some money, but it'll still be better to try directly to go to the left. That depends on what the difference is between the two rewards. So this is slightly more interesting. The other thing that you realize is once we have this stochastic domain, this non-deterministic domain, for example, the value of this state under the optimal policy is not so clearly defined anymore. Right? Because it's 0.9 times 91, but that only happens with 80% probability plus 0.1, whatever this value is, B star of A2 plus 0.1 times B star of A0. So we can solve that by sort of calculating this value function iteratively. And that's called the value iteration. So in order to be able to do that, of course, in order to calculate the value function, I have to iterate over all the states, right? Because every state has a value. Like there's a value function for A0 and A1 and A2 and A3. If I want to calculate the value function, I have to look at all the states. But now we are not only iterating over the states, but also iterate over the horizon. So basically, that means we use a dynamic programming approach to find the value function. V star of S. So we provide a we're sort of increasing the horizon for our iteration. So I add an extra subscript 0, which is the value of h at that point. So this is the optimal value for the state S when horizon is 0, which means we're not allowed to move anymore. So what should that value be? That means we're not allowed to move, we're not allowed to collect any rewards. So that has to be equal to 0. And the way that we model that is, just to be precise about the 61, the 91, what happens is we move into here, and in the next state, whatever action we execute, that will be our last action, and then we get the reward. Okay? That's why we get that one discount factor. So we don't get the reward when we enter B1, but we get the reward when we leave B1, except if we are in B1, then we can do any action we want. We will leave, we get the reward, but then the episode is terminated. And that's just so that the indices work out correctly. So that means if I'm not allowed to move at all, then the only value, then every state will have a value of 0. Because I can't do anything, I can't get any reward. So, but also I don't have to pay any money, so that's sort of good. So then, what should be the next step then? So now when we iterate, the next thing I want to calculate is V star of 1. So that's the optimal value for state S when H is equal to 1. Right? That's by definition, that's how we name the function.
Yes.
Yeah.
When we get the reward until we leave the state, or we will get it when we enter that state.
Uh, for this, it would be if I want the if I want 0 v star of b2 b1 to be uh, 0, then it must be if I'm in that state already, but I cannot move. I think it's when we enter, because our discount, yeah, it's sort of how I think it's easier to think about it when you leave that state, because otherwise, if you are in B2, right, and you move to B1, then do you get 91 or do you get 0.9 times 91? That's the question, right? If you get 91, then you will get the reward when you enter, when you take that action. If you get 0.9 times 91, then it would be when you leave it, because you get one discount factor. So if you're in B1, you get the full 91, because then you execute, right? So then you leave the state, you get the 91, no discount. If you're in B2, then you get discounted value. So conceptually, it's when you leave that state. So now I can take one action, right? I can do one action. So what that means is that if we're only dealing with a deterministic domain, then it will be the reward that I get from executing S dash. So ending up in state S dash plus the discounted reward of V of V star 0, if I don't have any more steps left, because now I used up one. So I want to pick the action A that maximizes being in S have a look at this. So underneath. Try that. Circle. Yeah, I don't know why that doesn't work for me, but it doesn't look so nice. The A is off to the side here instead of underneath. But okay, so this is for the deterministic domain. It's the best action I can take, the action A that maximizes the reward that I get, taking action A in state S, which leads me to S dash, plus the discounted value of state S dash. Right? But now it's a stochastic domain, which means this doesn't happen all the time. Right? So now this needs to be multiplied over the probability that I end up in state S dash, given that I execute action action A in state S, right? But now, again, there could be different S dashes. Right? So it's the maximum of A So with one step left, we want to maximize, we want to pick the action E that maximizes this sum. And that sum I get from the probability of ending up in S dash if I execute A in S, multiplied by the reward that I get, plus the discounted reward of the state that I end up with in next time. And I'm missing some brackets there. Where should the brackets go? This is not quite correct here. We need to have some brackets there. Because this is the probability that we end up. If we end up in S dash, this is the reward that we get for one step. So now Next, I want to calculate with two actions that I can take. So if I take two actions, so h is equal to 2, then I end up with this, 1. Because now I need to take the value of the state that I end up with, but from there I can take another action, right? I can take another step. So it's not v star 0 of s dash, but it's v star 1 of s dash. And then we end up with, you can recognize hopefully, the recursive definition of this function. We now have a definition of v star k, where v star k is equal to this, k minus 1.
Oh,
Yep.
does the comma need to like square or?
No, because that's only, from my point of view, that's only the next state. And this value then will be discounted if there's another reward further on down the line. So there's no gamma to the k or something like that. So it's just gamma. Where does the gamma to the power k come in? That's what we get if that's what we get if we recursively expand the value iteration. Because what I could do is let's take v star 2. Right? If I now, how would I calculate this? Well, I have an equation here, but that equation uses v star 1 of s dash, right? But luckily, hey, I actually know how to calculate this. Because that is, if I go back here, that's exactly what I have, right? V star 1 of s. So V star 1 of s is this. Let's call that max of A1. And this max of A2. S dash 2. S2. A2. S2. A2. S dash. S2 dash. S dash 2. So this will be A1 max S dash 1 S dash 1. Now this one is S dash 2 because it's that S2 that I need to iterate over. That's the way that I got there. And S dash 2 A1 2. And now we get another gamma here. So I sum up over the S dash 1. And here I sum up over the S dash 2. So sum of S dash 1, S dash 1 by S dash 2. This should be, yeah, that's correct. Then I go from S dash 1 to S dash 2, and then sum up over the S dash 1. S dash 2. So max A2, sum S dash 2. This is S. We want to execute A2. A2, we end up in S dash 2 plus maximum of getting S dash 1, and what we're executing from is S dash 2. I think that's correct now. And now that's where you get the multiple discount factor, right? Because now you have gamma squared basically on B star of 0. So if I project it for 2 steps, then I get gamma squared. If I project it for 3 steps, there will be gamma cubed. And and this is what we have here. Now, this recursive definition would allow us to calculate it. I could implement a function that uses this to calculate V star of h, where h is sort of a large value, 100 or something. We can talk later about how far, what v. What I really want here is the v of as h increases, right? 1 step, 2 steps, 3 steps, 4 steps, 5 steps. Question then is, how far do I have to go? 100 steps, 1,000 steps, 100,000 steps, a million steps? So that depends on the domain, the exact learning environment that we have. However, there's some important theoretical results that we know that still make that tractable. But first of all, let's think of, instead of having to go through all of this calculation, it's a little bit hard to follow, right? So now I'm going to pick a different function that we will implement. The function is well known. So here I now have a similar problem or a similar function, right? Except it's a lot easier to calculate because I don't need to reason about the actions and obstacles or anything like that. But what I have is a recursive definition of the function, right? So now this function will work. It will calculate the Fibonacci sequence. At least I hope it works. And what do we know about the Fibonacci sequence? It's generated by first two entries are 1, 1, and then the next one is the sum of the previous one and the previous one, right? The previous two. We add them together. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 13 plus 8 is 21, 21 plus 13 is 34. Okay? So this is a simple function, and yeah. Now, if you were to try and calculate this function using this definition, let's calculate the runtime, or what you would expect. I just always forget how to use Uh, A range up to 15, and y's equal to this, and t's is equal to that. That's yeah, that sucks a little bit now. I have to run it twice. Fibonacci of x. So what I want to execute, and number is equal to. So now usually you want to run the routine multiple times if you want to measure its execution speed on the computer and then get the average. But this one will take quite a long time. Actually, let me try 5 first to make sure it works. And okay, I'll make it fairer for the system. So I run it once and then I test it on the time measure on the next runtime. So the just-in-time compiler is warmed up and everything. And we shouldn't have so many issues with cache misses. So then let's plot. Let's plot x versus y's, x's versus y's with blue line. Label is equal to Fibonacci. Let's set title. Next label x or x. Fibonacci of x. This is the Fibonacci number value, and x2 is this. This is x. This is one time. that. Fibonacci. Ah, that one, I think it must be fine. Okay. Setup is equal to from main import Fibonacci. And here's our chart. And what can we see from that chart? Oh, this one not so much because it starts at 1 and then goes up linear. We want to run it a little bit longer. 15. Yeah. Not excess, but ease. So here we go in up to 0.00. And let's go to 25. See, now I got too ambitious. If you've seen the chart before, then the value of the Fibonacci number is, or the Fibonacci sequence, it behaves, as far as complexity is concerned. If you think about implementing a program and you want to solve Fibonacci of 100, then what kind of computer do you need? Yeah, give it a minute. Okay, 35 is it. And for the risky. One. 24 seconds. Good. So here's our. Funny. If you look at the value of the Fibonacci sequence, then what does that look like? Yeah, it's an exponential complexity, right? It's basically like a wall. If you're trying to solve anything over here with size 100, it will never be able to complete that. If you have a search space and your search space grows with the size of the Fibonacci sequence, um, then you're never going to be able to find a solution if your n is equal to 100. If n is small, then you can still search it. And it doesn't matter if you have today's computer or tomorrow's computer or access to a supercomputer or a computer that is 1 billion times faster than what you currently have, right? This exponential complexity basically shoots up like a wall, right? As long as your n becomes larger. So then you'd be looking at runtimes that would correspond to billions of years or even other astronomical numbers. Right now, for 35, we are up to 1 million. So, but what's more interesting is the runtime. The runtime goes up from basically nothing. All of a sudden, they're up to 1.75 seconds. So the runtime also follows a computation, an exponential complexity, right? But that really shouldn't be. Why is that happening?
Because we keep calculating the function we have already calculated before.
Correct, because we use the recursive definition, and in fact, we calculate every one of the functions multiple times, hundreds of times for f1, f2. Because in order to calculate f of 99, I calculate that of 98, 90, all the way up to 1, right? But in order to calculate f99, I again iterate all the way down to 1, and then iterate. And it's even worse because I calculate it twice, the whole recursive change, right? So if I want to calculate using this definition, if I calculate f of 4, then I have to calculate f of 3 plus f of 2, right? To calculate f of 3, I calculate what? f of 2 plus f of 1. So here, I calculate the same value twice. F of 1, F of 2. Actually, f of 2 is my base case. F of 2, 1 and 2 is the base case, so there's no recursive calling. So this would be 1. So I should do 5. F of 4 is f of 3 plus f of 2. And then this one is repeated there as well. And so that's how the whole computation blows up as well. But of course, hopefully, you won't be crazy enough to implement the Fibonacci number in that way. Right? How would you calculate the Fibonacci number?
We can create an array, so
Yeah. Or even better, you can use a list and just keep appending things. Right? That doesn't help you from the exponential complexity. Now, the basic system that we use, though, in this case, yes, we only use an array, and you can sort of think about it very simply. But the more general solution is called dynamic programming, where we can take we can apply dynamic programming whenever we have a solution that consists of subparts and the solutions to the subparts can be cached efficiently and the solution to the subparts are used multiple times during the computation. So how does that apply to the Fibonacci sequence calculation? It's probably the simplest example of dynamic programming principle that you can come up with, right? Because one, any kind, and this happens quite often, anytime you have a problem that's defined recursively, then implicitly there are subparts, right? So for the Fibonacci number, f of 5, I need to know f of 4 and f of 3. That just comes out of the recursive definition. But you can apply dynamic programming to other problems that are not given in a recursive definition. But anytime you have a recursive definition, by definition you have subparts. Right? Because in order to calculate the blob of x, I need to first calculate the blob of y and the blob of z. So now I have my subparts. So the Fibonacci sequence, yes, I already have f of n is f of n minus 1 plus f of n minus 2. Just in that definition, I already have two subparts. So clearly we have those, right? 2, what do we actually have to calculate in those subparts? The solution to the subparts are not the same, no. They're integers. And computers are very good at storing integers, right? So yeah, I can cache those results very easily. And do I have to reuse the subparts? Yeah, over and over again, right? Here, 4. Then 4 will calculate 3 and 2. And 3 and 2 will be repeated. So the lower ones are calculated over and over again. So, of course, it makes sense to cache those results. So that's a sort of prime example of dynamic programming. The next class we'll look at another example of dynamic programming, which is much nicer because it's not quite so easy. So how would you implement the Fibonacci sequence? You should, because we have 5 minutes, you can just implement the proper solution to how to calculate the Fibonacci numbers. And don't look it up on the internet, because that should be something that you can easily figure out in 5 minutes. And there's no trick to it. So let me just see, open up Python environment or Google Colab or whatever you have, and then at least calculate the Fibonacci numbers. We can try and use grapple.it. I mean, this is okay, you can do this, it's fine. But if you want to do some programming on the iPad, the only thing I found was this one. And it's still not a lot of fun to use, but it's an online environment that has C++ and Python and Java and Kotlin and whatever you want to do. Or you can use the collaboratory. But the collaboratory doesn't work so well on the Safari as the Chrome. So you don't have to watch him, you can do it by yourself too. Chop, chop, chop. Otherwise, I'm the only one that does the work here. Python environment. Make sure that you can write Python code too. You definitely want to install it on your own laptop for the class, unless you're very familiar with yeah, you need to add something to it. Yeah, you don't have any in yet. Like your fifth I doesn't exist yet, right? You have fifth 0, fifth 1, but fifth 2, start with 2, so fifth 2 doesn't exist. Right? So you actually need to change that to just append it. Yes, we don't actually need a list, but or an array to store it. But yes, so that's good. And we have other people joining. Good. This is a recursive approach. Um, if you have a look at reinforcement learning, 13, 21, 44, 112 plus 3 is 5, plus 5 is 8, plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 20 is 24, yeah. So here's how I would implement that. I use a list because I assume that I have to call Fibonacci multiple times. So I cache the results in an array. Initially, I just put the 1 ones in, and then if somebody asks me for a number that is past my array, then I add the necessary numbers, and otherwise I just return. I can just look up in FibList what that number is. Right? So this would be the dynamic programming approach, and here I think I changed it for so this definitely ran faster than the first time. And then here, oh, I wanted to say how come it took 1.6 seconds on 0, but no, it's 1.6 microseconds. So basically the runtime is 0.8 microseconds, right? As opposed to 1.x. What was it on the recursive approach? 1.75 seconds. So now I can calculate Fibonacci of n easily enough. Of course, the values still go up exponentially. But in order to see any kind of effect, apart from like random jitter in the microsecond range, I would have to greatly increase the Fibonacci. Like I'd have to calculate it up to. So here, 35, 50 already took several minutes, but now I should be able to calculate it up to probably a million easily. Well, maybe not that easy. I want to make sure I didn't. Yeah. Should just call Fibonacci 2. is oh, I used up all the RAM. Yeah, it restarted. Let's see what the student submitted. Oh, yeah. Um, the problem is that the NumPy array for a range here that cannot deal with the Fibonacci number up to 10,000. I could calculate it, but the but then I cannot convert the result to a 64-bit floating point anymore. But the calculation is fast. So this is 1 to the power of 208. And you can see the complexity curve. It is a booch. So that's it. Um, there's not even any branches there anymore. So once you're past 1,000, then computers that are trillions times faster won't make any difference. The complexity here basically goes from high, this is still a high number here, right? But compared to the ones coming up, it's nothing. So the complexity curve looks like this. So that means there's no way you're going to get over that wall. Doesn't matter, unless the only hope you would have would be if quantum computers work and you can somehow take that problem and convert it into a entanglement of quarks problem. But with standard von Neumann architecture kind of computers, not a chance, not even close. But you can see here the runtime basically, because I only need to append at the list actually, I only look at the end of the list, and looking at the end of the list is very efficient in Python. It's basically constant. Like there's a couple of outliers, but that's more like rearranging the memory. You can sort of see, because the Python doesn't actually use a list, like a linked list, like you learn in Computer Science 101. But lists nowadays in modern programming languages are almost always implemented as arrays and array lists. So you actually have a big block of memory that's stored as an array, and then if you need more, then you add extra blocks for this array so that you can dynamically throw it. The reason for that is because arrays are why are arrays much faster on a modern CPU? Why are arrays much faster than linked lists? The memory is sequential, and why is that important?
It's pretty fast to scan the data.
Yeah, sure. That's why the programmer. But why is it fast to scan the data? Because it sits in the cache, right? It's a continuous block of memory that you access all the items in that, or most of them in that block of memory. So when you access the first element of the list, it actually pulls in 64 kilobytes, 128 kilobytes, whatever your cache TLB is in your cache, right? So you get all of those, and they basically then are like free access, right? Whereas if you have a linked list, you need to access the element, then you need to look at the pointer, then you need to follow the pointer, but the pointer could be anywhere in memory. So when you access this block of memory, the processor is going to say, oh, I'm sure it's going to do something with that memory. So I'm going to pull in 64 kilobytes, or I don't know what the modern CPUs translation buffers for cache associative are. They are on the order of about 64 kilobytes. And then it's going to pull in all 64 kilobytes. Then you say, okay, now I want this piece of memory, because that's where the next element in your list is. So then the processor says, oh, so then it needs other memory, and it says, okay, then I get rid of this. Then now you have this load. But the next one will be again another cache miss. So the number of cache misses you have with a linked list is much, much higher, or in other words of saying it, the cache affinity of a linked list is much worse than that of an array. That's why for linked lists, people, if you don't have a cache, a linked list is much more efficient, you would think, because otherwise, if I need to insert an element, I need to copy all of the other elements one slot up, right? So if I have an array from 0 to 100, now I want to insert at the beginning, then I need to push everything up by one slot. Whereas with a linked list, I don't have to do any copying. But that copying is all through cache memory, so that's much faster than doing the linked list lookup. So that's why you actually have an array list. So if you look at the runtime here and you run this often enough, you'll be able to see what the cache line size is. Because every time I jump over, I need to allocate a new array list. That's where I will have a bump in my execution speed. All the other speed is going to be basically constant. So that's the effect that you sort of see. If we run this over and over again, you'll see these little bars show up. That basically then you can figure out what the cap size is of your processor. Not the level 1 cap size, but the translation buffer that you use, like how much of continuous memory is pulling in every time you make an access. More or less. Okay, good. So that's it for today. And we'll continue next class with another example of dynamic programming. So class is finished. What's next class? 28?
25.
25?